All right, let's talk about one of the most misunderstood, but also one of the most important ideas in all of science. We're talking about entropy. So let's kick things off with a simple question, a mystery you see play out every single day. Why do things in our universe only seem to happen in one direction?
I mean, just try to imagine watching this happen in reverse. It would look totally wrong, right? Like someone's rewinding a movie. We just know that a shattered vase doesn't magically pull itself back together. It's it's a one-way street.
Well, that distinct one-way direction that separates the past from the future, scientists have a name for that. They call it the arrow of time. And the reason it exists, the engine that drives it forward, is all because of entropy. Okay, so this arrow of time, what's really going on here? It's not just about things breaking. Let's dig in a little deeper and see how this fundamental rule of the universe shows up everywhere, all around us. Seriously, from the second you get up in the morning, you're swimming in these one-way processes. Think about it. Your coffee always gets cold, it never spontaneously heats up. Ice cubes in your drink, they always melt. And if you spray some perfume, those scent molecules spread out to fill the room. They don't just, decide to clump back together in the bottle. All of these things are irreversible. So what's the science behind all this? What's the rule? A lot of us were probably taught a really simple, kind of catchy explanation for this, but it's time we go a little deeper than that. You've almost certainly heard this one before. Entropy is just disorder or messiness. The classic example is the messy bedroom, right? It's easy for a clean room to get messy, but a messy room doesn't just clean itself. But here's the thing. That messy room analogy, it's a decent start, but it's not really accurate, and it can even be a bit misleading. For starters, messiness is totally subjective, isn't it? What looks like a mess to you might just be a very specific arrangement to a physicist. But more importantly, entropy isn't about how a room looks at one moment in time. It's about dynamic processes. It's about how energy moves and changes. So if the messy room idea is kind of flawed, what's a better way to think about this? Well, it really boils down to two key ideas: how energy spreads out and, believe it or not, simple probability. Okay, let's unpack those two concepts. They're the keys to really truly understanding what entropy is all about. First up, let's think about energy. A really useful way to picture entropy is as a measure of how spread out energy is. Energy just naturally tends to go from being all bunched up in one place to being dispersed everywhere. So you've got this hot iron ball in a cold room. All that heat, that thermal energy, is concentrated in the ball. That's a low entropy state. But it's not going to stay that way, right? The heat flows out, warms up the air, and spreads out until everything's the same temperature. That's a high entropy state. And that's really the first half of the definition, this natural, spontaneous tendency for energy to spread itself out as widely as possible. It's just what energy does. But why? Why does it spread out? Why is that the default setting for the universe? And the answer to that, well, it's just simple probability. This is the second and honestly maybe the most mind-blowing part of the whole thing. To get why, let's forget about energy for a second and just think about flipping a few coins. Check out this table. If you toss 4 coins, how many ways can you get all 4 to be heads? Just one way. Heads, 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 heads. But what about getting 2 heads and 2 tails? Well, look at all those combinations. There are 6 different ways that can happen. That means the mixed-up state, the disordered one, is 6 times more likely to happen than the perfectly ordered all heads state. And it's not because of some deep, mysterious force. It's just pure chance. It's just probability. And this, right here, is the statistical heart of entropy. The result you actually see, like 2 heads and 2 tails, that's what physicists call the macro state. The specific coin flips that get you there, like heads, tails, those are the microstates. So entropy is really just a count of how many microstates can give you the macro state you're looking at. A high entropy state happens not because the universe is pushing it that way, but simply because there are vastly more ways for it to happen. It's just more probable, overwhelmingly more probable. And because it's all built on the rock-solid foundation of probability, that makes entropy one of the most powerful and, really, one of the most unavoidable laws in the entire universe. This idea is so important it has its own name, the Second Law of Thermodynamics. All it really says is that for any process that happens on its own, the total entropy of the universe,
That's the system plus everything around it always goes up. Or, to put it another way, the universe is always moving from a less probable state to a more probable one.
Okay, but wait a minute. This brings up a huge question, a really fascinating paradox. If the universe is always moving towards more disorder, more probability, how in the world do you get something as incredibly complex and ordered as life? How can we even exist?
Well, the answer is all about the kind of system you're looking at. That second law we just talked about, it applies perfectly to an isolated system. Like a sealed, insulated box where nothing gets in or out. But that's not us. Living things are open systems. We're constantly interacting with our surroundings, eating, breathing, giving off heat. So here's how life pulls off its trick. It maintains its amazing internal order by basically paying an entropy bill to the rest of the universe. We take in low entropy, highly ordered energy, like food, and we use that to build and maintain our complex bodies. But in that process, we dump out a ton of high entropy, disordered energy back into the environment, mostly as heat. So while we create a little pocket of order for ourselves, we make the universe as a whole even more disordered. The total entropy still goes up, and the second law is safe.
And this whole cosmic accounting system, this trade-off, it doesn't just apply to life. It applies to the entire history and the entire future of the universe itself. You can actually look at the whole timeline of the universe as one grand story of entropy just increasing. It started in this incredibly hot, dense, and surprisingly low entropy state right after the Big Bang. Think of it like a tightly wound spring. Then we get to the age of stars, which are basically just massive engines that are fantastic at creating entropy, turning ordered matter into spread out heat and light. And what's the ultimate endgame? Well, that's what's called the heat death. Way in the future, when all the stars have burned out, the universe will just be a cold, uniform, dilute soup, a state of maximum entropy where, well, nothing really happens anymore. So instead of thinking of entropy as this depressing rule of decay and messiness, try thinking about it this way. Entropy is the very reason anything happens at all. It's the price of admission for a universe that has stuff going on. Without that constant drive toward higher entropy, energy wouldn't flow, stars wouldn't shine, life would be impossible. It is the cost of change, the cost of time itself. And it's the fundamental reason we have a past to remember, a present to experience, and a future to look forward to.